Today, I'll show you how to control a DC motor like this using Rust, so that you can use it in your next hardware project and race your friends to death.
This is the dual H bridge that we're going to use, and it is dual because you can control potentially two independent devices. You have output 1 and 2 on the left side and output 3 and 4 on the right side, and these can be independent devices. You use these 4 inputs here to control the H bridge. So 2 H bridges. Input 1 and 2 control one of the H bridges, and input 3 and 4 control the other. The last thing that you need to be aware of is that you power your high current or power electronics with these 2 terminals. If I set pin 1, so pin 1 to 3.3 volts, let's see what happens. We see that the motor is spinning on a particular direction. Let's see what it is. It is counterclockwise. Let's see what happens if we invert the pins. Let's see, this should be clockwise. And indeed, this is clockwise. So this is how you control the polarity or direction of the spin of your DC motor. I'm going to use GPIO, so general purpose input and output 5 and 6 to control the motor. Why? Because they are collocated and it's just easier to reason about them.
The simplest possible program that I can think of is, let's create a program so that the motor spins to the left for 5 seconds, then it stops for a second, and then it spins to the right. To achieve that, we'll use this C library. It is a C library, and we have wrappers for it. It's called gpio-cdev. The first thing we need to do is to initialize our connection to the GPIO chip. We get the lines, so the lines 5 and 6, like we said we were going to, set them as outputs. Initially, we set them to the false or off or 0 state. And then we need a couple of variables to keep track of what's going on in our program. We'll create a variable to keep track of the direction, and another variable to keep track of when was the last time that we inverted the direction. After that, we'll create a loop. So for those that are new to Rust, a loop is like an infinite while or an infinite for loop. Based on the current direction, we'll define the values of lines 5 and 6. We'll keep track of the duration since we changed the direction. And we'll say, well, if it's been more than 5 seconds, then go ahead and stop the motors. So that's what we're doing here. Change the direction. And finally, sleep for a second. I figure it will be cool to visualize what the program is doing by connecting an oscilloscope to the circuit. So here I connected a probe to GPIO 5 and another probe to GPIO 6. So we see that roughly each GPIO output stays on for 4 seconds, then it goes to sleep for a second, and then it alternates to the other pin. I recommend that if you are doing hardware projects, you want to validate your logic at the test level, within your Rust code. If possible, try to see your signals in an oscilloscope prior to actually loading the circuit with the real hardware. Less smoke, less tears is just better for everyone.
I'm proud of you.
Okay, so now let's make things a little bit more interesting. I want to be able to control how fast the motor spins. And to do that, the simplest way to do it with software is to use a PWM controller, pulse width modulation, the duty cycle. If you reduce the duty cycle, the time that the signal stays on, the motor will spin slower. Check this out. Here are the changes that we have to do to support PWM. The first one is we need a couple of constants. One to define the overall frequency of your PWM, and the other one is to define the duty cycle. Just as a reminder, this is the frequency and this is the duty cycle. So the higher the duty cycle, the closer to 100, the faster the velocity of the motor. Next, we need to add a little bit of math to compute the time that the pin needs to stay on and the time that it needs to stay off. And the last part of it is we modified the logic to turn off the pins so that we put the comparison if we need to let the motor rest when we turn off the pin. Oh, okay. So what you see there is all the pulses, all the PWM pulses going back and forth. And if I freeze this and then expand it, and we see that this system is pretty accurate. Granted, we are operating a very slow frequency. But yeah, roughly, it seems like the pin, the GPIO, stays on the high voltage for 1 square, which corresponds to 5 milliseconds, and it stays off roughly for 5 milliseconds as well. Roughly, this is not super pretty, but it will do the job for controlling a DC motor. When you want to go higher in frequency, there are some hardware optimized PWM circuits that we can use, and we can get into that. If you are interested in looking at that, let me know in the comments. I'm happy to dive into that. Here's the system with the PWM controller, and literally it sounds sadder. Check this out, this other video where I built an RC car using Rust and a little bit of Python, but don't tell anyone.